Okay, so let us start the next section or next part. So as I was mentioning, we are going to now look at two main properties of the moment generating function. The first one is uh, the moment generating function to get the moment generating function of a linear transformation of some random variable x. So suppose x is a random variable, it can be continuous or discrete. Suppose we know the probability mass function or the density function, or suppose we know the moment generating function of x. Let us say y is equal to a times x plus b, which is a linear transformation of x. Then we can easily obtain the moment generating function of y using the moment generating function of x as follows. Moment generating function of y is equal to e to the power bt, b times t, times the moment generating function of x evaluated at a times t. We can easily derive or prove this result, this theorem, uh, just by going through the definition. So let us do that. Um, so this is the second. Okay, the proof is not given here. So let me write down it here. It's very easy. You can do it by yourself also. So anyway, so let's look at the proof. So what you're looking at is MYT, right? So by definition, this is equal to expected value of e to the power y times t. But y is equal to ax plus b. So we can replace y by ax plus b is there. Then you have e to the power ax plus b times simple t. Notice here capital X, here capital Y t. So this is expected value of E x times at plus bt, right? So I can write down this thing again, expected value. Just this can witness it to the power expected value of x times at times e to the power bt, right? Because when you multiply to e to the power terms, the exponent adds up. So, but now notice here, this thing, b is a constant, t is a constant, so e to the power bt is a constant. Here, x is a random variable, at is constant, but then x is random, the whole thing becomes a random variable, right? So because this is a constant, I can take that out of the expected value. That's a well-known property. So let me take that out of the expected value. Then I can talk about expected value of e to the power x at. Right. Now we know that mxt is equal to expected value of e to the power xt. Right. So according to that definition, what you have here is the expected value of x times at. So therefore that part should be mx at. So therefore this whole thing becomes e to the power bt mx a times t. Right. So that proves the first result. Very easy. I'm just using the property of expected value. Okay, so that is the first important result. Now let's look at the second important result, which is useful when you are finding the moment generating function of sum of independent random variables. Suppose you have two random variables which are independent. Two random variables x and y are independent. Then the moment generating function of x plus y, which is denoted by m subscript x plus y evaluated at t, right? So x plus y is just a single random variable now, like w. So we are looking at m moment generating function of x plus y evaluated at t. We can prove that this is equal to the product of the moment generating functions if x and y are independent, right? So I have given the proof here, very easy again. So let us start by the definition. The moment generating function of x plus y evaluated at t according to the definition is equal to the expected value of e to the power t times capital X plus y, right? Now, if you just look at this part inside here, this can be written as e to the power tx plus ty, which is equal to e to the power tx times e to the power ty. So therefore, expected value of this thing is equal to expected value of this one, expected value of t to the power x times e to the power ty. Now notice that what you have is something like expected value of one random variable. Let me call it u times expect another random variable. Let me call it w. So you have something like this, e to the power u times w. And notice that we assume that x and y are independent. If x and y are independent, then u and w will also be independent, because this contains only x, therefore this is a function of x only. This contains as a random variable only y, so that is again a random function of y only. So this is a random variable, this is a random variable. You are looking at expected value of the product of two independent random variables. Because x and y are independent, u and w will also be independent, right? So from the result, first part, I think we learned this one is equal to expected value of u times expected value of w. So we can directly apply that to get this expected value of this quantity is equal to expected value of this quantity times the expected value of this one. Now, which is this one is mxt, and this one is myt. All right. So this one is myt. Right. So you can see that we started with this one. We were going to find out the moment generating function of x plus y evaluated at t when x and y are independent, and we proved that that is equal to uh, the product of the two moment generating functions. Actually, this can be extended not only to two, this can be extended to more than two random variables. Even if you have x plus y plus z evaluated at t, if x and y and z are independent, then it will be equal to the product of individual moment generating functions of x and y and z. Right. Okay, I want to get my arrow here. Okay, it seems I have to exit from this one first. Okay. Right. Okay, so this is what I have proved. I will just delete these things. Mm. I have to, okay. So it's not going away, but we are not about it. Will come again, right? So I have to, right. Okay, got rid of it. Now let us use these two results, actually the properties of the moment generating function to get expressions for the expected value, that is the first moment, And we will also get the expression for the variance that will need the first moment and second moment both. And we will also get, we will show some results regarding binomial distributions. Right? So let's look at this example. Suppose X has a binomial distribution uh, with number of trials equal to n and probability of a success equal to theta. So it says first find the moment generating function, hence derive the expected value of x and variance of x. And methanadi, I have forgotten to put this sign here. Because y has a binomial, sum of binomial m theta, right? I from and x and y are in. Okay. And suppose y, yeah, x has a binomial distribution with n theta. What I wanted to say is actually not this sign here. I wanted to say y has a binomial m theta, right? Not this sigma sign. I have somehow of a mistake, I think. Because in order to get this one, I have to, in latex, I have to type backslash sim. So here, instead of sim, I have typed, I think, sum. So that's why the sum has come, right? I should have typed here backslash sim backslash and then type sim to get this sign here. But what happened was I have typed backslash sum, then you get this one. So that's the problem here. So this should be replaced by this sign here to say y has a binomial n theta and x and y are independent. Then it asks me to identify the distribution of x plus y. Right. So let's do all these things quickly, just to show you the applications of the moment generative function. Right. So let us start with this one assumption. Suppose that x has a binomial distribution with n theta. So then we know that the probability mass function is given by this expression. This Pxx or probability x equal to x equal to this one ncx 0 to the power x 1 minus 0 to the power n minus x. This x goes from 0 to n, right? Integers and 0. So let's get the moment generating function first. The moment generating function by definition is equal to mxt is equal to e to the power tx. Right. So this tx is like a gx, some function of x. Right. So how do we get the expected value of some gx? We have to add gx times pxx, that is the probability mass function, over all possible x's. So when gx is equal to e to the power tx, we have to get this mxt will be then summation over all possible x's, that is x from 0 to n, e to the power tx. So this is gx, and this is the probability mass function, right? So now you can see that e to the power tx, theta to the power x can be combined to get this term here, theta times e to the power t to the power x. Then 1 minus theta and minus x. Right. Now, notice here, this is like, again, like a binomial summation. X goes from 0 to n, ncx. Right? This is like a to the power x, b to the power n minus x. If you remember the binomial expression that we discussed in part 1, you will see that this expression is equal to a plus b to the power n, right? If you expand a plus b to the power n, you will get this summation x from 0 to n, ncx, a to the power x, b to the power n minus x, right? So here's it's like a plus b to the power n, where a is equal to this and b is equal to this. Right. So therefore, this thing is equal to a plus b to the power n, where a is equal to theta e to the power t plus b to the power n. So this is therefore mxt is equal to this expression. So you can see now it is a function of t, and this can be defined. This will be this will exist for any real number t. So therefore, this mxt is given by this expression for any t real number, right? So that is how you get the moment generating function, right? So you'll have to use some tricks here, right? When you identify this, look at this, you have to identify that as this is actually a term like a plus b to the power n, right? Then you can directly write down this, right? Now, using this moment generating function, we will get expected value and expected value of x square and get the variance. So, as I mentioned, expected value of x can be obtained by taking the first derivative and putting t equal to 0. Right. So, the first moment, derivative, m dash x t is given by this expression. Remember, you are taking the derivative with respect to t, right? So, I don't have to explain this expression. But when you put t equal to 0 in this expression, you get n times theta, because this term becomes 1. So 1 minus theta plus theta, n minus 1, and then theta e to the power 0. So n times theta will be the answer. Here you have n. So expected value of x is equal to n theta. Very easily you can obtain from the moment generating function. If you want to get the expected value of x square, what you have to do is you have to differentiate this thing again with respect to t and put t equal to 0. When you do that, you will see that expected value of t square is given by this expression when you put t equal to 0. This is the the second derivative of mxt as a function. But when you put t equal to 0, you get this expression. So this is actually the expected value of x square, right? This is the expected value of x square. We know that the variance is equal to expected value of x square minus expected value of x whole thing square, right? So that means variance of x is equal to this term, which is the expected value of x square, minus the expected value of x is this one, the whole thing square. So when you put those two things, you get variance of x is equal to n times theta times 1 minus theta. Right? So like that, you can easily derive the moments around 0, as well as you can get variance from those two, first moment and second moment. Right. So that is one advantage of moment generating function. Now let us look at the second advantage. We are given that x has a binomial distribution with n theta. Y has a binomial distribution with m theta, right? Number of trials is m. So in that case, myt will be 1 minus theta plus theta to the theta et to the power m, right? Previous one, you had n here, right? Now we will use the result that we derived few minutes ago. That is, if x and y are independent, then the moment generating function of x plus y is equal to the product of the two moment generating functions. Right. So therefore, mx plus yt will be equal to the moment generating function of x times the moment generating function of y, which is given by this. Right. Now, what you have to do is look at this as a function of t. Right? This is a function of t. See whether this has the form of some moment generating function whose moment generating function is known. Right? Actually, we can see that this thing itself has this form. Right? As far as the function of t is concerned, this part is exactly like this. Only difference here is instead of n, you have n plus m. Right. So this is the moment generating function of a binomial distribution when parameters are m and theta. Right. You have n here, then you get the moment generating function. That is the moment generating function of a binomial distribution with n and theta. So according to the uniqueness of the moment generating function, we can say therefore this should be This is the homogeneity function of some random variable which has a binomial distribution with n plus m in place of n or m in the previous cases, and theta, probability of success. Number of trials is n plus m. Theta is still the probability of a success. So therefore, according to the uniqueness property, right, we can identify this as the form of the moment generating function of a binomial distribution with parameters n plus m and theta. So therefore, by the uniqueness of the distribution, uniqueness of the moment generating function, sorry, right, we know for a given moment generating function, there's only one corresponding distribution. So that distribution must be then a binomial distribution with number of trials equal to n plus m and parameter probability of a success equal to theta. So that tells us that x plus y must have a binomial distribution with n plus m and theta. Right. So that is theoretically how we derive or identify the distribution of x plus y when individual x and y have binomial distributions and x and y are independent. Now, this is theory. If we practically look at it, can it be true? If x has a binomial distribution with n and theta, what does it mean? X is the number of successes in n Bernoulli trials where the probability of a success is theta. So x is the number of successes in n Bernoulli trials with probability of success equal to theta. If y has a binomial distribution with m and theta, then y is the number of successes in m trials with probability of success equal to theta. So it's like tossing the same coin n times and finding out the number of successes and calling it x, and then toss it in again m times and finding the number of successes and calling it y, right? So what does x plus y give you? X plus y gives you the number of successes if you toss, right? If you toss the coin n plus m times. Right? Same coin, because therefore the probability of success is the same, theta. So x plus y should be the number of successes in n plus m trials, right? So we know that you should have a binomial distribution with m plus m as the number of trials and theta as the probability of success. So practically also, therefore, x plus y should have a same distribution binomial. So theoretically and practically, we can argue and get the distribution in that case. Very easily, practically also, we can guess, even though we don't know how to get it theoretically, we can guess the distribution in that case. But not always. Let's look at another problem. Suppose x has a Poisson distribution. So let's find out the moment generating function of x first. And let us again get the expected value of x and the variance of x. We already know, theory we have done. For the Poisson, expected value of x is lambda and variance of x is also lambda. But let's see whether we get those things using the moment generating functions also. And suppose y has another Poisson distribution with some other parameter, mu say, right? And suppose x and y are independent. So what should be the distribution of x plus y is the question, right? So in this case also, you might be able to guess the distribution by looking at the physical properties. We can also derive the distribution of x plus y using the moment generative function technique. Okay, so let's do that. So because x has a Poisson distribution, we know the probability mass function is given by this expression, where x can be 0, 1, 2, up to infinity. So the moment generating function by definition is this one. So let us apply that to this particular case. Expected value of e to the power tx is equal to the summation of e to the power tx times the probability mass function. You have to add over all possible x's from 0 to infinity. Right. So you can see that there is a cost. This term has x, therefore you cannot take it out or anything. But this has x in it, this has x in it. But this term doesn't have x in it, therefore you can take it out of the summation e to the power minus lambda. Now you have something to the power x divided by factorial x, where x goes from 0 to infinity. So again, you can use a certain identity that you have used earlier. You can identify this term as the tail expansion of e to the power this term, right? This part is the uh, tail expansion of e to the power lambda et, right? So therefore, this whole thing is e to the power lambda times e to the power lambda et, which you simplify that, you get this one, e to the power lambda et minus 1. Right. So that is the moment generating function of uh, the Poisson distribution with parameter lambda. Notice that this thing is also defined for any real number t. For any real number t, this exists. So therefore, we can say t is in R. Right. That is the moment generating function of x. Right. Now let us derive the expected value and the variance using this. Right. So expected value, in order to get the expected value, we have to take the derivative of the moment generating function once and put t equal to 0. So when you do that, you will see you will get lambda, right? Take the derivative of this is the derivative uh, of the moment generating function with respect to t once. So when you put t equal to 0, you get this thing becomes 1, this thing becomes 1, this thing becomes lambda. In order to get the expected value of x square, you have to take the second derivative. So see the second derivative and then put t equal to 0 to get the expected value of x square. So this is the expected value of x square. In order to get the variance, we can take expected value of x square minus expected value of x whole thing square. So that gives you lambda plus lambda square coming from here and then lambda square coming from here. So our final answer is lambda. So we already knew it theoretically. I have given you, but this is one way to get it, prove it. Get the moment generating function and then use the moment generating function to generate the moments, and then from those things you can get the variance also. Right. Now let's go to the next part. X has a Poisson distribution with parameter lambda. Y has a Poisson distribution with parameter mu, rate parameters, both cases. And suppose X and Y are independent. What is the distribution of X plus Y? Right. So we know the moment generating function now. So if y has a moment generating function with a parameter mu, then the moment generating function will be e to the power mu et minus 1. And because x and y are independent, moment generating function of x plus y evaluated at t is going to be the product of the two moment generating functions, which is equal to this one, which is equal to this one. Right. Now, check whether this has the form of a known moment generating function. Right? Look it as a function of t. Right? So you can see that this actually has the form of this one. Right? So you have e to the power t minus 1 like here, and you have some constant in front of that, e to the power. So e to the power, this term is there, and something in front of that. So therefore, this is actually of the same form as this one as a function of t. Right? So therefore, this must be the moment generating function of some Poisson distribution by the uniqueness property of the moment generating function. Right? This must be the moment generating function of some Poisson distribution. Which Poisson distribution? It should be the moment generating function of a Poisson distribution with rate parameter lambda plus mu. Lambda plus. So therefore, by the uniqueness property of the moment generating function, you can say x plus y must have a Poisson distribution with parameter lambda plus mu. X plus y must have a Poisson distribution. So that is theoretically how we prove it, right? Using the moment generating function technique. That is one technique. Practically, can you think of What is, if you say X has a Poisson distribution with rate lambda, how can you interpret it? So X can be interpreted as the number of events even in a given period of time, right? Say, for example, unit period of time. When the rate of occurrences, rate of events is lambda per unit period of time, right? Rate means unit period of time. If you say Y has a Poisson distribution with mean rate mu, so you are looking at a certain period of time. Maybe earlier you are looking at say T1 period of time. Now you are looking at T2 period of time. No, actually you are looking at the same time, unit period of time, because rate is defined for the unit no, usually, right? In other words, if you consider the same time length, right? Say for example, 1 hour, say rate is lambda in the first 1 hour, rate is mu in the second 1 hour, right? So X gives you the number of events, actual number of events occurred in the first hour with the rate lambda. Y is the number of events occurred in the second hour with rate mu. Then what does X plus Y give you? X plus Y give you the number of events occurred in the first 2 hours. So it again should have a Poisson distribution. What is the rate? Rate is equal to lambda plus mu. Excuse me. Right. So that's what we have got it here, right? From theory also, we have got it is as a Poisson distribution. The rate is equal to lambda plus mu, right? So like that, uh, in this case, theoretically we were able to prove. Practically also we were able to think. But practical distribution, deciding the distribution of x plus y practically is not always easy like this, right? For example, I will ask you to do the same thing for exponential distribution. For example, if x has a Poisson lambda distribution and y has a Poisson mu distribution, sorry, not Poisson. So suppose x has an exponential lambda distribution, y has an exponential mu distribution, and suppose x and y are independent, then x plus y will not have exponential distribution with rate lambda plus mu. If you say like that, that will be wrong, right? You cannot argue like that. So in order to get the distribution, you will have to, you can use the, not you will have to, there are other ways also, but you can use the moment generating function technique. And in that case, you will identify that x plus y has a gamma distribution instead of an exponential distribution, right? So in some situations, you may be able to argue and think of the distribution of x plus y practical terms, but not always. Always it is possible to derive theoretically, right? One method you can use is the moment generating function technique, right? So my time is over for this session also, therefore I'll stop here. I'll do a few more examples in the next part. Okay, we'll now start the next part of our lecture. In this part, I'm going to give you some theory with some proofs really, but just mention some theory for you to remember. These are usually very helpful. I'm going to give you some distributions of functions of random variables, mostly sum of independent random variables, and also sometimes linear transformations, linear combinations, and so on. Right. In the proofs, most of the times I'm going to use the moment generating function technique. Therefore, you will usually need the moment generating functions of the well-known distributions, right? You can easily find out the moment generating functions of well-known distributions from your internet. But I have here a collection of distributions, binomial, Bernoulli, hypergeometric, Poisson, geometric negative binomial for discrete, and normal, exponential, gamma, and so on for continuous. And I have given you the moment generating functions here, right? So these are well-known moment generating functions. We will use these to identify the distributions of linear combinations, linear transformations of these random variables. So I will be coming back to this table and the next table time to time whenever I need it. Right. So the first theorem is, suppose X has a normal distribution with mean mu and variance sigma square, and let Y be the linear transformation of X given by AX plus B, where A and B are constants, generally real numbers. Then we can show that Y also has a normal distribution with mean, of course, has to be A times mu plus B, and the variance has to be A square times sigma square, right? So the important thing is we are going to show that Y also has a normal distribution, and the mean will be coming from the property of the mean, and variance will come on the property of the variance. Right, so we are going to use the moment generating function technique here to show that Y has this normal distribution. Because X has a normal distribution with mean, mu, and variance sigma square, we know that the moment generating function from the table, you can get it. Moment generating function is e to the power mu t plus half sigma square t square. That is the moment generating function of X. Now let us find out the moment generating function of Y using the moment generating function of X. So, because y is equal to ax plus b from the previous part, I have shown that myd is equal to e to the power bt mx at, right? So, we will just substitute for this one and mxt is this one, therefore we know mx at is. So, when you substitute, you get e to the power bt and then e to the power mu at plus half square sigma square a square t square. Right. So when you simplify this, you get this expression, right? Now you have to see whether you can identify this as the moment generating function of some known form of a moment generating function, right? Notice that this moment generating function is a function of t. It has something times t, e to the power something times t, plus some other thing times t square. This also has the same form. This has e to the power something times t plus half something whole, all these things, something times t square. Right. So therefore, clearly, these both have the same form, moment generating function. Right. This moment generating function has the form of a moment generating function of some normal distribution. Right. In other words, these have the same form as the form of x. Only thing is that these constant terms in front of t and constant term in front of t square are different. Right. Now, remember that this is the homogeneity function of a normal distribution with mean mu and variance sigma square. Right. So mu is appearing as the coefficient for t. Half sigma square is appearing as the coefficient for half t square. Right. Variance is appearing as the coefficient of half sigma square. So same should happen here. The mean of y should appear as the coefficient of t. So you can see this is therefore the mean of y. This should appear as the variance of, because half t square is there, but only thing is different is here. So that should be the variance. So for y, variance is equal to a t square, a sigma square, a sigma whole thing square. And because this has the form of a normal distribution, by the uniqueness property of the homogeneity function, it implies that y must have a normal distribution with mean a mu plus b and variance a times sigma whole thing square, right? So that proves the theorem. If X has a normal distribution with mean, mu, and variance sigma square, and if Y is equal to AX plus B, then Y also has a normal distribution with mean A mu plus B, variance A square sigma square. So that is an important result. Let's look at now another important one. This is the linear combination of two independent random variables. Linear combination, right? So suppose x1 has a normal distribution with mean mu and variance sigma 1 square. X2 has a normal distribution with some mean mu 2 and sigma 2 square. And suppose they are independent random variables. And suppose A, B, C are some real numbers. And let's say Y is equal to AX1 plus BX2 plus C. So it's a linear combination. Right. And we can show that Y also has a normal distribution with the mean equal to A mu 1 plus B mu 2 plus C. And the variance will be equal to A square sigma 1 square plus B square sigma 2 square. Right. So to prove this also, we can use the moment generating function technique. What we are going to do is we are going to find out the moment generating function of Y using the moment generating function of x1 and x2 and the properties of the moment generating function and identify that the moment generating function Y is actually the moment generating function of this normal distribution. And that will, by the uniqueness of the moment generating function, imply that Y has this distribution. Right. Actually, I have not done it for you, but you can follow the method that I just mentioned, right? So you know the moment generating function of x1, you know the moment generating function of x2, and therefore you can get the moment generating function of y. Moment generating function of y will be what? So you have something here, some random variable plus another random variable plus a constant, right? And x and y are independent. So if you apply the two properties that we discussed earlier, right? If if y is equal to ax plus b, then myt is equal to e to the power bt times mxat. That is one thing. The other property is m of x plus y t is equal to mxt times myt if x and y are independent. Now you have here both of those conditions, right? You have two independent random variables. So AX1 is one random variable, BX2 is another random variable, C is just a constant. These two are independent. So if you apply the moment generating function technique, you will be able to show this result. So I will leave that as an exercise for you. The next one, the transformation of a gamma random variable. Suppose X has a gamma distribution with shape parameter alpha and rate parameter lambda. And suppose Y is some A times X where A is a real number. Just a constant multiplication of X. Right. Then we can show that Y has a gamma distribution with same shape parameter as X, but the rate parameter of Y will be lambda divided by A. Lambda divided by A, not lambda multiplied by A. If Y is equal to AX, Y has also a gamma distribution, but shape parameter doesn't change. Rate parameter now becomes lambda divided by A. Right. So you can prove that one also using the moment generative function because I have given you the moment generative function of a gamma distribution with shape parameter alpha and rate parameter lambda in this table here. Right. For the gamma, this is the moment generative function of a gamma distribution with shape parameter alpha and rate parameter lambda. Right. So now you have to look at, say, this is the homogeneity function of x, y is equal to a times x. So therefore, homogeneity function of y should be mx at, mx at, right? So what happens is you have to replace t by at. So now myt will be equal to lambda over lambda minus at to the power alpha. Right? Then you have to see it as again a function of lambda. Function of t as a homogeneity function of it's a homogeneity function evaluated at t. So you have to look at that one as a function of t. But you, in order to identify this, to check whether it has the same form, see whether you can write down the expression that you have now, that is lambda minus lambda over lambda minus at to the power alpha, as something divided by something minus t to the power alpha, or some other quantity here, some power. Right? If you can write down the homogeneity function of y as something divided by the same thing minus t to some power, then it will have the same form of a homogeneity function as the homogeneity function of a gamma distribution. So that's how you try to identify. Okay. So I think you can do it. See whether you can identify the homogeneity function of y as some term divided by the same term minus t to some power. Then it will have this form, and then whatever appearing here will be the rate parameter, whatever appearing here as the shape parameter, and it will be a gamma distribution. Right? Or it might have some other form. For example, if you get this kind of form, you will be able to find out what the mu is, what the sigma square is, and in that case, it will be a normal distribution, but it will not be in that case. And you will see that actually, according to the theorem says it has a gamma distribution. So you should be able to identify the distribution of y in the same form with some value here and the same value here and some value here. Right. So again, I'm leaving it as a homework. Right. So that's a constant multiplication of a gamma random variable. Now let us look at the sum of IID Bernoulli random variable. Suppose x1 up to xn are independent and identically distributed Bernoulli theta random variables. Bernoulli. X1 has a Bernoulli theta distribution, X2 has a Bernoulli theta distribution, and so on. So it can be considered as a random sample of size n from a Bernoulli theta distribution. And suppose y is the sum of those random variables, x1 plus x2 plus up to xn. What is the distribution of y? You can prove that y has a binomial distribution with n theta. N is the number of trials and theta is the probability of a success. For that, again, you can use the homogeneity function technique. So find out the homogeneity function of a Bernoulli random variable from this table. I have given you the homogeneity function of a Bernoulli theta random variable. So that's like, this is the homogeneity function of x1, this is the homogeneity function of x2, this is the homogeneity function of x3, because they are all identically distributed. That means they have the same distribution. Their homogeneity function should be the same. But because x1 up to xn are independent, then the homogeneity function of x1 plus x2 plus up to xn should be equal to the product of individual homogeneity functions. All right. So when you take the product of individual homogeneity functions of this form n times, you will get this whole thing to the power n. This whole thing to the power n. Right. And you will immediately see, then you have your homogeneity function of y will have this form, right? This thing to the power n. right? So if x's are Bernoulli theta, then y should have a distribution, whatever the distribution corresponding to this moment generative function, which is a binomial distribution. Binomial distribution. මෙතන වැරදිලා මම ගාලා තියෙන්නේ this is correct. Binomial. Yes, binomial. Right. So that will prove you that x1 up to xn summation has a binomial distribution because the product of this n times will give you this, and this is the moment generating function of a binomial n theta distribution, and therefore the y will have this moment generating function, and therefore y should have a binomial n theta distribution according to the uniqueness property of the moment generating function. And we discussed this in the class also, practically also, right? And I think you can remember that, right? And justify why sum of independent and identically distributed Bernoulli random variables should have a binomial n theta distribution, right? Theoretically and practically, you can explain that. Right. So this is that result, and then okay, this is not that result. This is the sum of Bernoulli. Now let us look at sum of binomials. They are independent. Suppose x1 up to xn are independent random variables where with xi has a binomial mi theta. So x1 has a binomial distribution with m1 theta. x2 has a binomial distribution with parameter m2 theta. They are not parameters m actually, because usually they will be known numbers, but theta will be a parameter. Like that, xn has a binomial mn theta, right? But notice that we are saying that they are independent, but they are not identically distributed because the distributions are different. But here we are considering independent random variables. And let y be the sum of these independent random variables. We can prove that y also has a binomial distribution with the number of trials equal to the sum of m's, m1 plus m2 plus up to mn, probability of a success equal to theta. So because you know that x1 up to xn are binomial random variables, you know the moment generating function of x1, you know the moment generating function of x2 up to moment generating function of xn, all are known. Right. Now, because y is a sum of independent random variables, the moment generating function of y will be equal to the product of individual moment generating functions. Right. So when you take the product of individual moment generating functions, you will see that the moment generating function of y has the form of the moment generating function of a binomial distribution again, with some value in place of n and some value in place of theta. Right. So from that you can show that y has again a binomial distribution. Right. So I leave it again as a homework. You can do that. And now let's look at the sum of independent Poisson random variables. We already looked at sum of two independent Poisson with rate lambda 1 and lambda 2. I'm extending this one here to n random variables. Suppose x1 up to xn are independent random variables with xi having Poisson lambda I distribution. Right? X1 has a Poisson lambda 1 distribution, x2 has a Poisson lambda 2 distribution, and so on. So they are independent, but they are not identically distributed because the distributions are different. Let's consider y to be the sum of x1 up to xn. Right? Then again, using the moment generating function technique, we can prove that y also has a Poisson distribution with the rate now is equal to the sum of the rates of x1 up to xn. So that again, you can easily prove using the moment generating function technique. Right. The next result, suppose you have again IID geometric random variables, right? X1 up to Xn are independent and identically distributed geometric random variables. They are independent and identically distributed as well. That means all of them have the same distribution, and therefore they all have the same moment generating function as well, right? So you know the moment generating function of x1, you know the moment generating function of x2. They all have the same moment generating function. You can get it from the table. And then you can find out the moment generating function of y using as the product of the individual moment generating functions, because these x1 to xn are independent. And you will see that the moment generating function of y has the form of a moment generating function of a negative binomial distribution, right? The moment generating function of a negative binomial distribution is also given in the table. So if you compare what you got as the moment generating function of y, you will see that it has the same form of the moment generating function of a negative binomial random variable. So thereby, again, you can identify what the value of uh, R in the negative binomial distribution, what is the value of theta in the negative binomial distribution, right? And by the uniqueness property of the homogeneity function, y must have then a negative binomial distribution with the corresponding R and corresponding theta, right? So you find out what the R is, you will see that R has to be n, and then uh, theta is the same as the previous probability of a success, right? Suppose that x1 up to xn are independent random variables. So this is the next theorem. Suppose that x1 up to xn are independent gamma random variables. They are not identically distributed. We are not, you can consider identically distributed. That means in that case, everything will have the same gamma. But here we can go more general. We can allow alphas to be different, but same lambda, right? So if you have a situation like that, several gamma distributions with different, possibly different shape parameters, but with the same rate parameter. Then again, using the homogeneity function technique, you can show that the sum of x's, say y, will again have a gamma distribution. With now the new shape is equal to the sum of the individual shapes, shape parameters, and the rate parameter is the same as the same previous rate parameter. This again you can prove very easily using the moment generating function technique. Okay. So I think that is a good place to stop this part, because now in the next one, I'm going to talk about a very important theorem called the central limit theorem. For that, I need to show you some examples also. Therefore, I will stop this part here and we'll come back and discuss the central limit theorem in the next part.